Hey everyone, my name is Sujay, and I'll be talking to you today about data mesh at Netflix. This is our paved path platform for stream processing, and how I'll talk to you about what led to data mesh, how it was built, and how it has democratized stream processing and real-time analytics at Netflix. A little bit about me. I'm currently in the data platform team at Netflix, working mostly on real-time data infrastructure. So a lot of Kafka, Flink, also working with Iceberg, Elasticsearch, Druid, and platforms like that. I was earlier at Meta in the data platform team there. And before that, I was with Microsoft working on large-scale distributed systems, working on Azure for a little bit. So I'm really interested in data platforms, distributed systems, data analytics, as well as real-time machine learning of late. So a quick overview of what we will talk about today. We will go over stream processing, what it is, how do we handle stream processing at Netflix, then what data mesh is. We would look under the hood of how data mesh works, how it's built, and talk a little bit about our operations and the learnings from the journey that we've had. So Netflix, as many of you might know, we are present in over 190 countries. We have over 300 million active subscribers joining us, watching their favorite shows from all of these different locations in the world. When they're doing that, they're also using over 1 billion devices to watch Netflix. And as you can imagine, some of this scale and geographical distribution leads to unique technical challenges. Today, we are going to dive a little bit deeper into how some of the data processing that powers the Netflix experience happens. So at a very high level, what is stream processing? Stream processing is the processing of data in motion. That is, you're performing computations on data as it is being produced or generated. Usually, this type of paradigm is used with real-time data. And imagine when a Netflix user is browsing their homepage, it's generating a ton of user activities and a stream of events, which can then be processed for intelligence and analysis. So how is stream processing different from batch processing? Usually, in stream processing, you would model your data as an unbounded stream, so that the stream has a start, but it does not have an end. However, in batch processing, usually your data set would have a start and an end. And this difference can have some implications on how you reason about the completeness of the result, the order in which you process the data, etc. So let's talk about stream processing at Netflix. One is called change data capture. Change data capture is the process of capturing and identifying and capturing any updates on a source database, and then delivering them downstream to different systems in real time or near real time. At Netflix, for example, our operational data stores are the system of record when it comes to domain objects. And it's often very important for us to ensure that the downstream systems have an up-to-date copy of the data, so that the decisions that are being made using that data are always using the latest and the freshest data. Often in change data capture or in streaming in general, you may also want to do some transformations as the data is moving from the source to the destination. So you may want to filter out some records, you may want to do some projections, or even complex transformations like aggregations or joining the data before it lands into the destination. The other large category of stream processing applications we see is when the data is produced by microservices or different applications. So instead of now the source being a database itself or change feed from database, the source now is basically event producers, which could be other services or applications. And then this source lands into a data streaming pipeline. You perform some computation on top of it or do some processing, and then land the data into a data store. So as you can see, there's a lot of microservices in our ecosystem, and they generate a lot of data. And all of this data needs to be transported to a place where it could be processed and analyzed. At a very high level, there's a lot of user features that are powered by stream processing at Netflix. Stream processing is used in personalized recommendation, the impression history. We've ventured into games lately, so a lot of real-time game analytics uses stream processing under the hood, and traditional use cases like fraud detection, as well as advertisements, etc. Bridge two compute platforms, Apache Flink and Apache Kafka. As many of you may already be aware, Apache Flink is an open source distributed processing engine, which is used for stream as well as batch processing. And Apache Kafka is a distributed messaging system. It's pretty much the de facto standard when it comes to streaming and message queues. So we leverage these two heavily at Netflix. And then if someone was to write a stream processing application at Netflix, they have two options. They could either build their own custom Flink job. They can do this using the stream processing as a platform, stream processing as a service platforms, PaaS, where they would build their application, use code, typically Java or Scala, to build their application, and then they would manage it and run it and operate it themselves. Or they could use data mesh, which is a more abstracted, low code, no code way for users to build streaming data pipelines and be able to do processing. Let's quickly talk about the custom Flink jobs. So if you were to build your own custom Flink job, then you would use this PaaS platform. You have access to the low-level Flink data stream APIs, so which gives you granular control and access to like state, timers, watermarks, and it's very powerful if you know what you're doing. And as I mentioned, the app needs to be built and managed by the app owners. So if you are building your own custom Flink job, then you have to develop it, you have to deploy it, then you have to operate it, right? You have to handle the upgrades and alerting and monitoring, etc. So the team who's building it needs to be well versed with the streaming ecosystem as well as okay with managing all of these applications. So if you were to write your own Flink job, you have access to low-level constructs which give you very granular control over what you could do. Our sparse control plane is well integrated within the Netflix ecosystem, so it's easy for you to write up the job and then integrate it into the ecosystem. However, writing your own Flink job also has a steep learning curve. You need to be familiar with the streaming ecosystem, be familiar with the Flink data stream APIs, how do the streaming connectors work, etc. And then, of course, there's a cost on managing and operating these jobs. Basically, anytime there's a security upgrade or alerts, etc., they need to be taken care of. So that brings us to why we needed data mesh. At Netflix, we are processing over 14 trillion records daily. And as you can imagine, like building all of this and building streaming pipelines for all of these use cases and having them managed by different teams can become pretty challenging at scale. In general, there's a steep learning curve when it comes to streaming data pipelines, and there's an immense operational overhead. So we realized that there was a need for a unified approach. And the challenge here really was, how do we bring all of these excellent streaming capabilities, make it available to all of these different teams at Netflix without needing them to really understand the details of stream processing and understanding the low-level details. And that's mainly the inspiration of data mesh, and that's where we see most of its value come from. So data mesh is the paved path for data movement and processing at Netflix. And this is a fully managed streaming platform. Think of it as a place where you can come build streaming pipelines, and it's managed for you by the data mesh team. So now we'll start diving a little bit deeper into data mesh itself, and let's start with the building blocks of data mesh. So at a very high level, we have the data mesh sources. These data mesh sources are where the data enters a data mesh pipeline. This could be a Kafka topic where some application is producing events to, or these could be backed by CDC connectors for databases like RDS, CockroachDB, etc. Then you have a set of processes provided by the platform for transformation. Today, the data mesh platform provides SQL processor, where you can write SQL queries to do transformation on your data, as well as the other one you see here is the GraphQL processor, which can be used for enriching data via some DGS. If these don't work, data mesh also provides the capability for a team to build a custom data mesh processor, which is tailored to your needs. And then finally, there are the data mesh sinks, which is where these are the processors or the Flink jobs which are writing data to the destination data stores. At Netflix, we use Elasticsearch, Iceberg, Kafka, and then we're constantly evolving these source and destination connectors, and that's a value proposition of data mesh as well. That these source and destination connectors are always growing. And just a quick recap, like the source, think of these as essentially Kafka topics where the data is landing, and then the processors, the transform as well as the sync processors are essentially Flink jobs. So this is an example data mesh pipeline. On the left-hand side, what you see on the left is the data mesh source, where the data is coming into the system. Then there are some transformations that are being done on the SQL processor. In this case, one is an Iceberg sync and the other is a Druid sync. And the DAG could also be fairly complex. And as you can see, the team who created this pipeline, they are doing some processing using SQL and then using GraphQL to do further enrichment, and then that data is further being transformed using a SQL processor. So data mesh gives you this capability, and at all of these hops, you have the ability to basically start consuming from any of these intermediate hops. So as a managed stream processing platform, data mesh provides a bunch of capabilities out of the box. We have observability built in, which means that all of your data mesh pipelines are being constantly monitored. We have alerts on it. There's certain auto remediations built in. I'll go into this a little bit more later on, but the platform can remediate common faults that exist. Security is built in, so we follow the standards recommended by the internal security team. Schema is a big part of data mesh ecosystem, where we'll go into this a little bit as well, but schema is an essential aspect of data mesh, and we have schema evolution end to end. The system auto scales, which means that if there is an increase or decrease in traffic, the compute, the cluster size the job sizes can automatically evolve to adjust to that traffic. And then we have a rich connector ecosystem, right? Like I mentioned, we have a lot of these source connectors like RDS, Cockroach, and then sync connectors like Druid and Iceberg. And this is always evolving based on the business need. So what you saw in the UI or in the previous slides was a logical DAG for a data mesh pipeline. And this is what you saw. You saw the producer, which is the data mesh source. You saw the SQL processor, as well as then the data landing into a couple of sinks. Underneath the hood, what is happening is that this logical DAG is then translated into a physical DAG. And here you have basically a Kafka topic that acts as the data mesh source. Then the SQL processor is the Flink job, which is doing the transformation. And then the output of the SQL processor goes into another Kafka topic, which then becomes the input for the Iceberg and the Kafka sync processors. These processors then process and transform the data and then write it to the external data stores. And then the output of the SQL processor goes into another Kafka topic, which then becomes the input for the Iceberg and the Kafka sync processors. These processors then process and transform the data and then write it to the external data stores. Going a level further, you also now have schema at every hop. So basically, you have a schema defined at the producer, which is your output schema. That then becomes an input, the input schema for the SQL processor. Now, SQL could be doing some kind of transformation on the data based on which the output schema of the SQL processor could be different, and that's inferred by the system automatically based on your SQL query. Then the output of the SQL processor, output schema of the SQL processor becomes an input schema for the two downstream processors. And then there's the specific schema for the data stores as well. Let's take a moment to just understand the different aspects of schema here. So schema starts with the schema definition and registration. So the producers of the data would register and define a schema at the source, and we use a centralized schema registry to store these schema definitions. Then the schema that's been defined needs to be enforced, and the enforcement happens at the producer. So as the data is being produced, the schema is the data is validated against the schema that's registered for the data mesh source. So we prevent any data that doesn't match the schema from even entering the source, the data mesh source or the Kafka topic. And then the schema needs to be also validated by the platform, because once the data enters the store, the source, there is a downstream data mesh pipeline which has schemas defined at every hop, and it's the platform's responsibility to ensure that the schema is valid all through the pipeline. Schema propagation is also a key aspect, which means that once the producer defines the schema at the data mesh source, it's the platform's responsibility to then propagate that schema downstream through all the intermediate processes all the way to the sink data stores. And then we also have automated schema evolution. So data mesh allows you to modify your schema in certain compatible ways. And then we have enforcement to make sure that the schema evolution follows these rules. And if it does, then we automatically evolve the schema from the source all the way to the destination. So that's an overview of data mesh. I'm now going to talk about some of the key aspects of the data mesh platform, that especially the ones that we've built lately. So what was happening was we were seeing a lot of these data mesh pipelines, and then where people would sync data from the source to the destination or do some simple transformations. However, more and more we were seeing the need for complicated transformations, complex transformations, for that our users wanted to do before landing the data into the data store. And the options available were fairly limited. You would have to write your own custom Flink job or a custom data mesh processor, which are both of which are pretty heavy lift, and they require a decent amount of streaming expertise. So the team decided to invest in Streaming SQL, and that's where the SQL processor came into the picture. So with the SQL processor, the idea is that you can very quickly, if you have a data mesh source, then you can attach a SQL processor, write your SQL query. You have the ability to sort of iterate on the query, and you're using a very familiar language to do data transformation. And as you write your query, your schema, output schema, is automatically being inferred, and it's being validated. So you have a very quick iteration loop. And then you could basically, in this particular view, you can see an enrichment happening via the SQL processor. So you have an incoming data, and that data is being enriched via an iceberg table. So you could do fairly complex transformations as well. And we are seeing a pretty heavy usage of SQL. Initially, we thought this would be for simple transformations like filter and projection, but we are already seeing people using JSON functions and doing various types of casting, and also a lot of demand for stateful transformations. We also have the ability. Data mesh started as a UI UI was the main interface for our users, where people would come to the data mesh UI to define the data mesh pipeline. But recently, we've invested in configuration of pipelines as code, which allows you to create and manage your data mesh pipelines via YAML. And we're actively working on a Druid sync. Druid is used for real-time analytics. It's getting more and more usage at Netflix, and we think that data mesh being part of the streaming ecosystem, such an essential part of the streaming ecosystem, it makes sense for us to make it easier for our users to be able to use Druid for for landing their data and doing further analytics. Let's talk about the scale. So, data mesh is processing about 100 million events per second on an average. We have close to 8 trillion events daily. We have over 5,300 streaming pipelines, and this translates to over 20,000 Flink jobs and 25,000 Kafka topics. So as you can imagine, like managing all of these pipelines, so many different jobs, does require investment in the operational side as well. And also, we are growing pretty rapidly. Like the number of pipelines that are being created is growing at a rapid pace. So what's the secret to keeping these many pipelines and all of these processes running without making our on call a nightmare? The key that we've learned is automated operations as much as possible. So as a team, we've invested a lot in automating our operations. I'll talk about a few of the key ones here. One important one is autoscaling. So autoscaling, because the streaming data doesn't necessarily follow a particular pattern, and there can be bursts of incoming traffic as well as troughs. So it is essential for us to be able to adapt to that traffic pattern however it's happening, and scale up the Flink jobs as needed and scale it down so that we're not wasting compute. So our auto scaling system essentially does that. It keeps an eye on the key metrics like the resource utilization or the consumer lag on Kafka and automatically scales the Flink job. This it saves us a lot of manual intervention, right? So it makes our on-call easier, but also makes sure that the resource utilization is up to date and it's efficient. Then we've invested in automatic remediation. We have a pretty comprehensive system called fault management, which automatically like diagnoses the faults that are happening in the system. As you can imagine, with these many Flink jobs and Kafka topics and pipelines, things could be breaking. There could be transient errors every now and then. So the fault management system acts as the first responder, and it can take action on some of the more like well-known common issues and remediate them already. So it reduces the mean time to recovery, also leads to less on-call pages. Monitoring and alerting is, of course, an essential part. So we have standardized dashboards and metrics for all data mesh pipelines, and having these in a standardized way makes it easier to have visibility into all different aspects of the system. We also perform upgrades. The platform team performs upgrades for the data mesh pipelines, so the Flink jobs and the Kafka clusters. This takes away this burden from the users. So if there is an urgent security patch, we have the capability to roll that out pretty quickly, and it also ensures that as we are improving our platform, everybody is getting the benefits of the platform. And then in addition, we have a bunch of tooling around schema and Kafka. With Kafka, we have to constantly do capacity management. There are situations when we may need to move the Kafka topics between clusters, and we have sophisticated tooling for all of this. So what are the learnings from our journey? I think one key takeaway is just the value of higher level abstractions, because they can lower the barrier to entry, and it can take away a lot of operational overhead from the other engineering teams. And we can have focused tooling and standardized key patterns. it's very important to establish well-defined contracts with the users. Our users are from very different parts of the Netflix engineering and data science team, everybody with a different level of understanding of streaming and different use cases. So it's important to build a product that caters to all of them. We've also found a lot of value in, rather than waiting for a finished product and waiting to deliver that, engaging early with customers, getting their feedback, and using that to help improve our products. And guardrails, I think this was a learning with the SQL processor, because SQL is very powerful. You could do a lot with SQL, so we've invested in guardrails so that only operations that we are comfortable operating are allowed on the processor. All right, so that is it. Please check out our blogs on data mesh on the Medium Netflix Medium page, as well as I'd love to connect if you are curious about this space or if you're working in this space in general. Thank you.